Hello. So the first video lecture will be on orthogonal complement, and the setup is the following. V is a vector space with inner product. Which, as usual, I will denote by these angled brackets. And then what we're trying to do is to use the notion of orthogonality to solve a certain problem which has important applications in other areas. And the problem is approximately of the following nature. If you have a certain set or a subspace of V, you would like to compute the shortest distance from a given point to that subset, or the subspace that is spanned by that subset. And the distance can be computed either, the usual distance given by the dot product if you are working with Rn, or it could be some more exotic inner product that you have depending on the problem. So to get to the problem itself, we have to introduce a certain notion which is called orthogonal complement, and this is crucially used in the actual solution. Alright, so this is the setup. This is the vector space with an inner product, and then U, let me also erase this part. U is a subspace, and then we define the orthogonal complement. Orthogonal complement of U in V, and this is denoted U is the sign, perpendicular sign, is the set so what's the definition of the set? This consists of all elements V in V, such that the inner product of U with V is 0 for all U in U. Okay, so is the set consisting of vectors in V which are orthogonal to all vectors in U. Right, and let me just check that you can see it in the camera. All right, so that's fine. All right, so let me draw a picture of what this looks like. So suppose we are in Rn. Example, we are in let's say R3, so that I can draw a picture with usual dot product. And suppose U is a line. So U is a line and it goes through the origin. Now think about all vectors in R3 that are orthogonal to this line. So one such vector is this one, and another vector is this one, or any scalar multiple. And then you can, of course, rotate this out of the plane. Yeah? So imagine that once you start rotating this line, you're getting a plane. So a picture would be what you end up getting if this is U. Then the orthogonal complement is the plane that consists of all vectors that form 90 degrees with this particular vector. So all vectors in this plane are perpendicular to U, or maybe a better picture would be to imagine this being U, and this is U prep. Okay, so something like this. So this rotates and you get a plane, as I said, and I redrew the picture there, and this is another view of the same picture if I sort of shift my point of view. All right. So unfortunately I cannot stop and ask if you have questions, but as I mentioned in my announcement, I will have Skype office hours, and once you watch the lecture, you can join the Skype discussion group, and you can ask if something is not clear, and I will explain again. Right, so the first some properties of this orthogonal complement, this is theorem. The first is that this orthogonal complement is a subspace. Subspace of B. The second property is that U and its orthogonal complement, if you intersect them, you get the zero vector. Okay, and then there is a certain third property that I will give once I prove these two. These two are relatively easy to prove. We have already seen this on the given example, because in the example, in the previous example, U is a plane. Through 0, 0, 0 in R3, so it's a subspace, hence a subspace. And we also saw that the line and the plane that is perpendicular to it obviously intersect only in one point, which is the origin. So that's this statement. So the 0 is the zero vector. Now let's formally prove this theorem. So I will erase this remark. Okay, proof. Well, let's think about what this statement means. For a subset to be a subspace, two properties have to hold. The sum of two vectors in that subspace should be in the same subset, and the scalar multiple of a vector in that subset also should be in the same subset, right? So, so suppose V1 and V2 are in this orthogonal complement, and we want to show want to show v1 plus v2 is also in this orthogonal complement. So what you do, you have to take an arbitrary vector of u, that u in the subspace, so there is a small u, there is a capital U, let u be an arbitrary vector, and we need to show that this v1 plus v2 u is 0. Okay, but this is very easy because by the properties of the inner product, this is equal to, but then this is v1 u plus v2 u. Right, so this part is equal to this, and there's a question mark. So we're trying to prove this. Let me again check that you can see at the bottom of the blackboard. Alright, so this is again fine. Right, and v1 and v2 are in the orthogonal complement. So each of those, by definition, is 0. So this is equal to 0 plus 0. Which of course gives you 0 as we wanted. So this shows that the sum of two vectors here is again in the same subspace, and then similarly you can prove that the scalar multiple of a vector here is in the same subspace. So that part I will leave to you. Alright, so now let's erase this part and prove the second part. And the second part is even easier. So we want to prove that only the 0 vector is in both u and its orthogonal complement. So suppose u, well, a small u is in capital U and the same u is in orthogonal complement. Right, then by definition, then u, because it's in the orthogonal complement, the inner product of this u with any other vector in u itself has to be 0. So, and because u is also here, you get that this is 0. But by the properties of inner product, we know that the only vector that gives 0 when you take the inner product of the vector with itself is the 0 vector. So this implies, by definition, of inner product, that u is 0, as was required to show. Alright, so now let me erase this theorem and state the next important theorem, which tells you that a V is actually a direct sum of this U and its orthogonal complement. So remember what direct sum means. Recall that this means every vector in V can be written as V equal u plus w, where u is in U and W is in the orthogonal complement. And moreover, it can be written uniquely in this form. And this decomposition is unique. And then early in the course, we proved that this uniqueness part, that V can be uniquely decomposed in this form, is equivalent to U and the orthogonal complement not intersecting each other. So this part, not the decomposition part, but the uniqueness part, the uniqueness is equivalent to the intersection of these two spaces being 0, and this we already proved. So because we proved this, it is enough to show this part. So we will show that every vector can be decomposed this way. Okay? Alright, so let me erase this. And also this part. Alright, so before I give you the construction, which itself is quite important because it will be used in the definition of orthogonal projection. So let's go back to the example that I discussed and see how this theorem applies to that example. So if you have R3, right, and say U was a line, and this is the orthogonal complement, then the statement of the theorem says that R3 is a direct sum of U and the orthogonal complement, which is more or less clear. For example, you can imagine that U, the orthogonal complement, is the xy plane and U is the z plane. If U is z plane, z line, z axis, then perp is xy plane, and simply what the statement of this theorem says is that if you have a vector in R3, you can uniquely write it as xy 0 plus 0, 0, z, which is now is clear, right? So we're trying to prove this for general abstract vector spaces with an inner product. All right. Now I didn't mention this at the beginning of the lecture, but throughout everything we are assuming that V is finite dimensional. When it is not finite dimensional, then you have to be careful with some of the statements I will be making. So assuming that V is finite dimensional, then U is finite dimensional. Yeah? And then I will now state a fact that we will prove slightly later. We will prove next time. So U has an orthogonal basis. This is a fact. This will be proved. Will be proved later. So this is the Gram-Schmidt process. It's not just a proof, but it's an actual construction of such a basis. This is Gram-Schmidt process. Okay, so let's use this fact. Let U1 UM be an orthogonal basis of U. And remember what this means. This means that these vectors, this set of vectors, form a basis of U, and they are orthogonal to each other. So, i.e. U1 UM is a basis of U, and UI UJ is 0 if I is not J. So we choose such a basis, okay, and then so let V be in V. Again, we want to decompose this V into a vector that lies in U and a vector in the orthogonal complement. So the part of V that belongs to U uses the inner product, and this is the important part that will be used in the construction, in the actual calculation of the orthogonal projection. So what you do is that define this vector U, which is given by you take V with U1. So this is some number, and then you take the inner product of U with U, and then you multiply, so this is a number, and you not multiply U1 by this number. And then you add to this V U2, 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 and so here U1 changed to U2, and you continue doing this to the last element, which is V UM UM. So this is my U. And I will keep it here. So there is an important formula that you should remember, or at least try to, well, it's not hard to remember. You take the vector that you started with, and you take the inner product of V with all the vectors in this set, and you divide them by the length of the vector. In the textbook, you will notice that this part is missing. The reason is that in the book, the basis is assumed to be orthonormal, which means that every vector has length 1. There is really no difference between choosing orthogonal or orthonormal, because if you divide a vector by this inner product, you get the normalized version of the same vector, which has length 1. So if I change this to the same basis divided by the length of each vector, then I will get an orthonormal basis. But it's a matter of preference whether you normalize at the beginning or you just work with a orthogonal basis. Both have their advantages. Mainly the advantage of just working with orthogonal is that the orthonormal basis in the examples usually has to involve fractions, and I don't like it. All right. So let's continue. This is U. So for V, we define this U, and then you define W to be V minus U. Again, where U is this guy. Then obviously V is U plus W. Right, so this part is obvious. It is also clear that this U belongs to the subspace U. U belongs to this U since it is a linear combination of basis elements of U, of the capital U. Yeah. All right. So this U is in U. V is decomposed this way. The hard part of the proof, or the hard part is writing down this U really, but we still have to check that this W belongs to the orthogonal complement. So we need to check that W belongs to the orthogonal complement. And for this, it is enough to check. Alright, so let me leave it here. This U. So I erase this part. So what does this mean, that W is in the orthogonal complement? It means the W is in the orthogonal complement if and only if W, what do I want to denote? Not the same U, but U prime is 0 for all U prime in U. Okay, so we want to check this, and now this W was this is equivalent to V minus U prime being 0, because W is V minus this U, right? And this is equivalent by opening this inner product to V U prime minus U prime being 0. So we want to show that for any element of U, right, this inner product is equal to this inner product, where U is this element. So this is equivalent to VU prime equal UU prime. Now, we can expand this U prime in terms of the basis. This is A1 U1 plus AM UM. So you can always do this. And then these inner products, right? So then v u prime becomes a1 v u1 plus am v um. So here I'm assuming that we're working with real numbers, otherwise you have to take the complex conjugate. Assume we're working over R. But with over complex numbers, the proof is the same, except that when you put this expression instead of u prime and expand, these coefficients will come out as complex conjugates. And then the same you do with this part. So this is u prime, so this is equal a1 u1 plus am um. So it is enough to show actually that these parts are equal. So we want, let's show that the inner product of v with u1 is the same as the inner product of u with u1. Right, because if each of them individually is equal to the part in this inner product, so if this is equal to this is equal to this, then the sum itself is equal. The sums are equal, so this expression will be equal to this expression. That's a simple observation. So it remains to actually compute u and u prime. So now I will do it for u1. So enough to show that v u1 is equal to u1. The argument for other ui's is the same. Well, it is enough to show, let's say, this for all I. And then we will do this for I equal 1. The argument for other elements is the same. All right, now I erase this part.